the camera.
We'll bend the pin straight. Okay, safe?
The safety is removed and this grenade is ready.
Everybody ready? 3, 2, 1. That's a good shot.
This time, the camera is able to capture a better image of the plume.
We could definitely tell by the size of that fireball how big it is. You know, we actually use the post. We know the post is exactly 6 1/4 inches wide, and then we spot our software on that post, and then move out to the plume size, and the computer tells you the distance across.
This plume ends up having a diameter of 4.1 feet. Ken will pass this data on to law enforcement, who will decide if it's safe enough for residential use.
You don't use grenades every day. So you might use them maybe once a month or once every couple of months, or maybe only once a year. So if you had training, maybe say once a month or once every quarter, you could see this, and you know, it would just keep it fresh in people's minds that, hey, this is not a toy. It's less than lethal or non-lethal. Might not kill you, but it's hard to be a cop with one hand or no hands or part of a foot missing, or, you know, so it is a good training tool in that aspect. It shows you what can happen.
We've all heard the saying, faster than a speeding bullet. Now, Beretta is making it possible for us to see that speeding bullet by using a high-speed camera. Engineering a gun that shoots flawlessly is something Beretta USA takes great pride in. If a misfiring or jamming gun were to make it to the marketplace, it would be a devastating blow to the company's nearly 500-year history as a high-quality gun manufacturer. Not to mention a possible life or death situation for the men and women carrying them. When developing new pistols, they use high-speed cameras to analyze every detail of how they fire.
I'm David McCallum, and this is Beretta USA.
At their only U.S. plant located in Accokeek, Maryland, David is the Vice President of Manufacturing and Engineering. Here, they manufacture 4 different types of pistols.
Here at Beretta USA, we make the Bobcat Tomcat family of small pistols, the PX4 subcompact, the Neos target pistol, and the M9 pistol for the military.
In 2009, they estimate they'll make about 116,000 guns, many of which will be used by the police and U.S. Armed Forces. All of them are machined, hand-assembled, and tested here on the premises.
We focus on manufacturing 3 major components for the pistols. The frame, which is this part here, comes in as an aluminum forging, and we machine it.
This forging goes through several phases of machining.
And it comes out as a finished frame, which we 100% inspect to ensure quality, and it functions in the field.
After painting and heat treating, all the other major components meet up in the assembly room.
So everything comes to this room, and we assemble the pistols by hand.
Then they head to testing.
These are guns that are ready for testing, so this is where we do the 1 magazine commercial and 2 magazines for military, and they're tested in that back room right there.
But before any gun even makes it to this point, they go through several phases of development.
In the process of designing a new gun, it's basically 3 steps that we start with. We construct a model, a 3D model with our CAD system based on the specifications that we've worked up from an engineering standpoint. At that point, we do an SLA, which is basically a plastic model of the gun, more so to determine if it feels right in the hand and it looks like we think it's going to look like coming out of the 3D model. At that point, we'll go into hard prototyping, where we'll make actual prototypes that we can fire. And it's at that stage that we'll use the high-speed camera to verify 2 main issues. The main thing we want is the gun always to function as it's supposed to, because we view that as a safety item, whether it's a commercial user or certainly in the case of the military user or the law enforcement user, we never want the gun to jam. And there's 2 ways it can basically jam.
Issue number 1 is making sure the gun pulls the spent shell out of the barrel, then ejecting it out of the gun correctly.
And the other piece we're looking at is to make sure that as the bullets, which are in the magazine, feeding up this way, that they feed back into the barrel correctly and that there's no chance of the bullet jamming when it goes into the barrel or a chance of the bullet jamming with the bullet that's following it beneath in the magazine.
A bullet leaving a Beretta 9mm pistol is traveling at speeds of 1,000 feet per second. The spent shell isn't traveling that fast, but flies out of the gun at a fast rate. So fast that it's hard to get a visual of how it's reacting when the gun's fired.
So what we'll do is do the high-speed camera work there and make sure that, and we'll see that when we film it later, that it's ejecting properly, that the timing that we've calculated in our engineering calculations are correct, and we don't have to change any of the linkages in the gun.
Using a high-speed camera is the only way to see the details. Beretta's resident gun tester is Arthur Pecson. He set up a demonstration of a standard gun test and fills us in on what he's hoping to capture with the high-speed camera.
When the empty case is extracted from the chamber and hits the ejector, and you can see the empty case fly out. It's important that the case ejects consistently. We've noticed on some guns that you can have erratic ejection.
He's ready for the first test using the Beretta PX4 Storm 9mm pistol.
Ready. 1, 2, 3.
In real time, it's difficult to analyze any details of the ejecting shell, but in slow motion, new details are revealed. When the bullet is fired, the spent shell ejects in a fraction of a second. If a jam were to occur, it would happen at this precise moment, as the gun ejects the spent shell and reloads. Then the recoil forces the gun back. Arthur sees no erratic ejection this time. But he sets up for another test. This time, he'll fire consecutive shots. The purpose is to make sure the spent shells are ejecting with the same trajectory. Spent shells ejecting in different directions is an indication that an engineering calculation may need to be corrected, sending a gun back to the drawing board. Arthur fires 3 times. All 3 shells have identical trajectories, indications of a perfectly engineered pistol. After the prototype passes initial testing, they'll manufacture about 1,000 pre-series guns.
From that group, we'll pull 100 of those and go through all the test firing and also do reliability and durability testing on the system. And it's important to do it in both cases, the first one to make sure the design is correct, and the second one to make sure that the manufacturing process that we've set up and that we're going to deliver into the field is working correctly.
These are just a few of the tests Beretta puts their guns through, but the only ones that can't be seen with the naked eye. IMR Test Labs is an independent material testing firm in Portland, Oregon. One item they test daily is steel.
Over the years, we've done product testing on everything ranging from mountain bikes to fuel cells to artificial hips.
Doug Puerta is the vice president and technical director at IMR, and one of their clients is a pipeline manufacturer.
The test we do for them is called a Sharpie impact test. What a Sharpie impact test does is to measure the impact strength of material.
The Sharpie test has been around for over 100 years and has been instrumental in helping build ship hulls, which was a problem with many early ships.
Remember the big ship, the Titanic, that sunk? The Titanic was made of steel, and when it was designed, steel was a perfectly normal selection. Unfortunately, they didn't predict the behavior of the steel at reduced temperatures. So when the Titanic sailed into very cold waters in the North Atlantic, the properties of that steel changed, such that when it hit an iceberg, the steel actually cracked instead of buckling, and when it cracked, we all know what happened after that.
That's why pipeline manufacturers test the strength of their pipes at varied temperatures.
When we look at our pipeline customers, their pipes can wind up in all kinds of different environments. They can wind up in the Alaska, they can wind up in the Midwest, they can wind up in a very arid and hot region. So to understand the properties of these pipelines in different environments is very important. You can't manufacture a pipe and assume it'll function the same way in Alaska and in Arizona. So that way, if a pipe is subjected to any kind of sudden shock, whether it be an earthquake or a truck backing into it, we want to feel confident that pipe is not going to brittly fail.
To do this test, the manufacturers send IMR sample pieces of steel.
Here we have a very small section of a very large pipe. You can tell by the curved surface. Again, what we're doing is removing a specimen from this plate, which we can evaluate the mechanical properties.
What we have here is a Sharpie impact tester. It measures the toughness of the metal. When the hammer's in the all the way upwards position and locked, it has 100% of potential energy. When it swings down into the downward position, right before it hits the specimen, it has 100% of kinetic energy.
Simply put, this test measures how much energy it will take to fracture the steel. In a real-life situation, the energy could come from a backhoe that accidentally hits a buried pipeline.
As it passes through the specimen, the hammer height and the result of that strike gives you a foot-pound or a measurement of the hardness of the particular specimen that you're testing.
The first test will measure the toughness and strength of our sample at room temperature. With the high-speed camera, you can see the hammer as it hits and fractures the specimen.
Okay, so we came up with a reading of 140 foot-pounds.
Now that we've seen that, why don't we try doing one in a cryogenic bath?
So reduced temperature.
Soaking the specimen in the cryogenic bath lowers the temperature to -300 degrees, simulating the harshest conditions the steel will face. This test should have dramatically different results.
Coming down.
Colder steel is weak and brittle, and the explosive impact easily snaps the sample in half, which only takes 10 foot-pounds of force. That's a fraction of the energy used to break the room temperature sample.
On a regular basis, we look at specimens after they've been tested using microscopy, but having the ability to do high-speed video during an actual test is a benefit to us because we can witness the failure actually occurring.
Seeing how the steel easily fractured after a cryogenic bath tells Doug and Sean that this sample is not suitable for use in extremely cold temperatures.
And one of the biggest advantages doing testing before the product is released out in the field is that we can discover problems here that might crop up later on and be much more expensive to find and or fix.
If a pipe is going to fail, it's better to fail here, rather than a situation that could be hazardous. From guns, grenades, NASCAR, and banks, ultra-slow motion is unveiling the secrets of speed and safety, slowing our world down, and giving industries a chance to move even faster. With billions at stake and speed the name of the game, there are thousands of hidden worlds still waiting to be discovered.